Okay, it's 5:30, so let's go ahead and get started today. So welcome everybody to our next virtual lecture. So this is our first one after the spring break. So first off, before we start anything today, I just want to ask how everyone's doing. Hopefully, I know some people were telling me about their spring break before, but for those of you just joining, how's everyone's spring break and how's everyone doing?
Doing pretty good. Hanging in there, trying to stay positive.
That's good. Yeah, definitely got to stay positive during this time. I think it's really easy to kind of get down with everything that's going on, but as long as you have a positive attitude and taking all the necessary precautions, I think that's kind of the best thing that you can do in the situation. Everyone else doing okay?
Yep.
Cool. Well, hopefully you guys are doing well. Hopefully this is something that we're going to continue on as best as we can throughout this semester, and hopefully this will be something that that will be a little bit of normalcy in your life. Okay. Okay, so with that, let's get started. So before we get back to diffusion with finite volumes, which was the kind of the topic that we left off on before the spring break, I want to talk about just some administrative stuff. So mostly regarding the project. Okay. So for those of you who have looked at the project already, you know that there's quite a lot of Matlab development that goes on with that project. So originally, I was, that was a project that I was thinking of for a long time throughout this semester, and what my hope was that because there's a lot of Matlab development, that I would that we'd still have access to the classroom somehow, and I'd be able to help you. This was kind of before a lot of the coronavirus stuff started going down. So now that the we don't have access to the lab, and it's much harder for me to kind of be more hands-on with the with helping you guys with MATLAB. I think I'm going to change up the project a little bit, because even though I provided the starter code for you guys, there's still quite a lot that you guys have to do within that starter code in order to get it working. Basically to do the video that I showed you guys right before we took off. So what I'm going to do is I'm going to modify the starter code to kind of give you a much bigger boost than what's currently there. So basically what I'm thinking is I would basically put in most of the structure of the code, and then what I would want you guys to do is I mostly just want you guys to fill in kind of the coefficient values. So I would kind of indicate pretty clearly, I'd have all the lines of code written. You just have to, I'd probably have some kind of dummy phrase in there called like insert coefficient here, where you would insert the proper coefficient. So you'd still have to, work out some of the problems a little bit by hand just to, get the proper value of the coefficient. And then you just have to input that into MATLAB. So I'm going to make that modification for you guys, okay? And then besides that, another thing that I'm going to do is I'm going to modify the deliverables a little bit, so there's not as much that you guys have to do for the project, because even with the code the way it is, even with the full solution, it's going to take some time to run all the simulations in order for you to get all the plots. So I'm going to cut down the requirements on that so that there's less that you guys have to do for that. And then one suggestion that someone gave me just this morning was going over the code together in the class. So I think so today I'm going to save that for Wednesday, because today I want to finish up the topic on diffusion with FVM, just because it's going to be on the midterm for next Wednesday. So so this Wednesday, what we're going to do at the beginning of class is we're going to go over the project code, the new starter code that I need to make probably sometime tomorrow, just so you guys, it's clear for you guys kind of where I want you guys to put stuff in. And kind of what's going on with the starter code, because I know there's a lot going on in that code, and I think it'll be really helpful just to go through it together as a class, just so you guys kind of know what's going on. Okay. And then one other small thing. Oh, you have a question?
Oh, quick question, Professor. Did you plan on doing this on Wednesday just so I can get my MATLAB set up and everything for that?
Yeah. Let's do this on Wednesday.
Perfect.
Yeah.
Thank you.
And one other thing, I don't know if. So I looked at the project specs, and I don't know if we settled on a due date for kind of everything, but I think originally what I had planned was to have you guys turn in the project on the day that we were supposed to have our final exam, since we're not having a final exam in this class. But I want to push that back probably to the Monday after finals week, because I still need some time to grade them. But I want to give you guys as much time as you need to basically work on the project and basically ask for help as much as you can. So I'm going to push the, I don't know if we set a due date yet, but I'm going to push that back kind of as much as I can, just to give me enough time to grade it so I can put grades in before they're due. Okay. So basically, we'll talk about all that on Wednesday. Today I was kind of working on other stuff, so I didn't get to, figure out the details, but Wednesday we'll talk more carefully about that and about going through the code and, just so you know when everything's due. Okay. Okay, so that's the project. So are there any other questions on the project? Okay. So the other piece of info that I want to talk about is the midterm. So we have one more exam in this class. So that's scheduled for next Wednesday. And I think we talked about it briefly before the spring break, where we talked about how it's going to be basically a take-home midterm. So I'm going to upload the exam basically at 5:30 next Wednesday, and then you guys are going to have 24 hours to complete it. So that time limit is mostly just to give you guys flexibility, because I know everyone's kind of dealing with different things right now with their health and with their family and financially. So I want to make sure that you guys have enough time to do the exam, without impacting other aspects of your life. So I think before the spring break, we talked about how I might modify the exam based on the new time limit, and I've kind of decided against that. So the midterm is basically going to be kind of the same format as the first midterm, where there's going to be no Matlab involved with the midterm. It's just going to be theoretical stuff, so developing the equations based on what we went over in the class. Okay. So there's going to be two homeworks. There's two homeworks that I'm basically going to test you guys on. There's going to be homework 4, which is the unsteady stuff, which is the homework that you turned in right before spring break. And then I posted a new homework basically over the spring break on diffusion with finite volumes, which is going to be due next Monday. Okay. So basically after today, we'll be finished with diffusion with finite volumes, so you'll have everything that you need to do that homework. But basically, if you can do those two homeworks, then you'll do pretty well on the exam, because my midterm exams, I don't have them be cumulative, so you don't have to worry about stuff kind of before basically everything that we covered for the first midterm. So it's basically just going to be stuff that we covered ever since the first midterm, and it's going to be just theoretical stuff, no MATLAB at all. Okay. All right. Are there any questions on the midterm exam? Okay. So homework 5 is posted. So I know that was kind of hidden in that explanation, but make sure you guys take a look at that. That's due a week from today. The time limit for the midterm exam. So the midterm exam, you guys will have 24 hours to do it. So I'm going to upload it at 5:30 p.m. Next Wednesday, and then it's going to be due 5:30 p.m. on the Thursday, the next day, basically. So you have 24 hours to do the exam. Okay. Any more questions on project, midterm exam, or the homework? Okay. So if you guys logged into Titanium at all over the spring break, what you noticed was I was kind of trying to upload as much stuff as I could. So I spent the spring break basically trying to get as much ahead of the prep as I could, because I know things are really challenging right now. So I want to make sure I get the content basically out to you guys as soon as I can. So basically, whenever you guys have time, you guys can look over the notes and get ahead when you can. So I mostly with this, the motivation to give you guys as much flexibility as possible, I think, because now I think everyone's schedule is going to be kind of uncertain. So if I can get the material out to you guys sooner, then I think that'll be a plus for everyone too. Okay. Also I posted a study guide for the midterm too. So so just like we did for midterm 1, there's a study guide on Titanium for you to look at to help you prepare for the midterm exam. Okay. So as you're studying, definitely take a look at that, and that'll help you out as well. Okay, so let's get started. So where we left off last time was 2D diffusion with finite volumes. Okay. So I think where we left off was, we were trying to evaluate the diffusive fluxes on our element, right? So for a 2D case, we have basically a square, right? And then on our square, what we were doing was we were evaluating integrals on the boundary. Okay. So if we label the sides of our square with each of the compass directions, we have the north face, we have the east face, we have the south, and then we have the west. And then what we were trying to do after we applied divergence theorem to our finite volume equation was we were trying to evaluate this integral right here. So we have minus k integral of the gradient of phi dot n ds. Okay. And then what we said was that this is basically a line integral that goes around our entire cell. Okay. And then the way that we were going to evaluate this is we're going to break it up into 4 different integrals. Okay. Basically one for each side of the square. Okay. And so if you do that and you apply basically our integration, our trapezoidal rule, and then we apply this this dot product here, we're left with the following expression. Okay. So we have minus k, and then we have d phi dx on the east face, delta y, plus d phi dy on the north face, delta x, plus d phi dx on the west face, delta y, plus d phi dy on the south face, delta x. Okay. So we got this expression basically after we applied, we broke this into 4 different integrals, and we applied basically our trapezoidal rule to integrate this at the centroid, right? Because remember, when we're doing finite volumes, we usually don't like to perform these integrals. We usually approximate them with the trapezoidal rule. Okay. And so what we need to do is we need to take this expression here, and then put it in terms of the cell-centered values, right? Because the thing with finite volumes is we're not computing things at the grid points of our mesh anymore. We're computing them at the centers. Okay. So remember, we gave that the symbol phi sub c. Okay. And so what we're going to do is we're going to take this expression here and put it in terms of the cell-centered value phi c, and then all the neighboring cell-centered values, phi on the north, phi on the west, phi on the east, phi on the south. Okay. Okay. All right. So that was kind of just a very quick, just kind of just to remind us where we were at the end of last time. Are there any questions on this before I wipe the board? Okay. I'm going to wipe the board. Okay. So let me kind of draw out kind of the typical case. Right. So the first thing we have is our cell. Okay. So the value of the solution in the cell is phi sub c, right? And so adjacent to this, we have all of the neighboring cells. Oops. Okay. So here we have the phi north, and we have phi east, phi south, and phi west. Okay. So I'm using capital letters here to basically denote that these are cell-centered values. Okay. Whereas in the previous board, basically I used lowercase to denote values at the face. Okay. So if you remember from the previous expression, what we hope to basically compute are the derivatives at each of the faces. Okay. So we need things like this. So we need d phi dx at the east face, right? And then d phi dy at the north face. We need d phi dx at the west, and then d phi dy at the south face. Okay. Right. So here I used lowercase letters to denote these are at the faces. Okay. So the face values are basically right here. Okay. Use a different color actually. Okay. So the face values are basically evaluated at the blue X's right there. Okay. So basically what we need to do is we need to basically approximate these with the self-centered values. Okay. Question? Well, can you repeat? Your audio is breaking up. Can you repeat that?
Oh, sorry. Does the order matter on how you set up your equations?
Yeah, so since we're adding them all together, the order doesn't matter. Yeah, good question.
Okay.
Okay. So actually, let me do this. Let me color code this a little bit better. Oops. Use the technology that's available to us. Okay. So let's use red for the east face. Oops. Right. Let's use yellow for the north face. Let's use green for the west. And then let's use blue for the south. Okay. Okay, so let's start with the east face. So on the east face, we need to do d phi dx. Okay. And remember what we did for the one-dimensional case was we used basically a center difference scheme or a finite difference scheme to approximate this. Okay. So the way that we're going to express d phi dx on the east face, we're going to do phi capital E, right, minus phi c all divided by delta x. Okay. Where remember we're using capital letters here to basically denote the that these are self-centered values, right? So these aren't values at the face. So basically what we're saying is that phi e minus phi sub c, and then you subtract those two and you divide by delta x, and that's basically going to be the slope of the line that passes through this this face right here. Okay. Okay. So then continuing on with that same trend, so d phi dy is going to be at the north face going to be phi capital N minus phi capital C all divided by delta y. Okay. And then d phi dx at the west face is going to be phi sub c minus phi capital W all over delta x. And then d phi dx or d phi dy at the south face is going to be phi c minus phi s all over delta y. That's a y. Not much better, but that should be a y. Okay? And so basically what we're going to do is we're going to take these expressions and basically plug that in to our finite volume expression, which we had on the previous board. Okay. Question?
Yeah, I see how you got the equations for east and north, but how come for west and south you went off the middle? Is there a specific reason, or?
Yeah, that's a great question. So the you know, like Jorge observed, you know, for the east and north, we put kind of the neighboring face first, and then our centered face second. But for the west and the south, we put the centered face or the centered value first, and then the neighbor value second. And so the reason for that is because the east here is on the right. I remember usually for our x-axis, we go from left to right. So when we compute the slope, we usually put the one on the right first, and then the one on the left second, right? So for the east, that means we put phi e, which is the one on the right, and then we subtract that from phi c, which is the one on the left. Okay? But then if you compare that to the west face, on the west, our west neighbor lies to the left, right? So in order to compute the derivative, we do phi sub c first, and then we subtract phi sub w. Okay? And the same thing for the north and the south. So for the north, we have our upper value, we put our upper value first, and then we put the lower value. And then, so for the north face, that's north minus south. And then, but for the south, since our south is higher than the south face, we put south minus south. Right. Does that make a bit more sense?
Yes, thank you.
Cool. Right. Any other questions before I wipe this board and move on?
Yeah, quick question. You said the capitals letter denote what again?
Right, so the capital letters denote the values at the cell centers. So the cell centers are basically where these X's are going to be. Because with the finite volumes, we need to make the distinction between values that are evaluated at the faces, which are when I say faces, I basically mean the boundaries in between the cells. And the cell centers are going to be the solution values that are at the actual centers of the cells themselves.
Got it. Thank you.
Yeah. Okay. Any more questions on this before we move on? Okay. All right. So if we plug in those derivatives into our integral expression, we get the following. So we have minus k integral of del phi dot n ds. Okay. So this is the overall integral that we're trying to evaluate. So this is the integral over the entire boundary of our cell. Okay. So we plug in those the values from the previous board. We get the following. Okay. We get minus k. So minus k is still there. Can't forget him. Okay. And then we have the value of the derivative at the east face. So that's phi e minus phi c all divided by delta x. Okay. So that's the value of our x derivative at the east face. Okay. And then additionally, we also have a delta y out here. Right. And remember, this delta y comes from the trapezoidal rule, which is the length of that face. Okay. So remember, you can't forget both. So remember, the delta x is from the derivative, the delta y is from the trapezoidal rule of the integral. Okay. Plus, and then we have the derivative on the north face. So we have phi n minus phi c all over delta y. Okay. So remember, that was on the north face, we evaluated a y derivative. Okay. And then we're going to multiply this by delta x. Okay. Let me put parentheses around these guys just to make it more clear. Plus, now we have the derivative on the south face, which is actually, we did a minus out here. Minus. Right, so we have a minus phi c minus phi w all over delta x multiplied by delta y. And then finally, we have the derivative on the south face. So we have phi c minus phi s all over delta y, because it was a y derivative. And then multiplied by delta x, which comes again from the trapezoidal rule of integration. Okay. Okay. Right, so there's a lot of terms in there floating around, but we can simplify this. Just by the usual assumption, we assume that our grid is uniform. So that means the spacing in the x direction is going to be the same as the spacing in the y direction. So let's assume that delta x is equal to delta y, and we'll say that it's equal to some delta. So this delta represents this space in between the cell centers in our grid. Okay. So if we do that, all the deltas here are going to cancel out. And then we're left with the following expression after we simplify a bit. Okay, so we have minus k phi e plus phi w plus phi n plus phi south minus 4 phi c. Okay. Let's put a box around this guy. Okay. So that right there is our finite volume equation for the derivative. I mean, for the diffusion term. Okay. So hopefully this should look familiar, because this is this is basically our second time looking at diffusion. So our first time was with finite differences. So if you compare this basically to our finite difference coefficients, back when we did finite differences, you should see that these are basically the exact same coefficients, except in finite differences, we call them the upper neighbor, the lower neighbor, the left and the right. Now we're using compass directions east, west, north, south. But we still get the coefficients of 1 on the neighbors and then a -4 on phi c. Okay? And that's by design, because remember we're basically solving for the same phenomenon. So no matter if we use finite differences or finite volumes, we should get the same answer. Okay? Right, so this is our diffusion FBM. Okay. But what's kind of key here is kind of how we approach this. And actually, once we start doing the boundary conditions, which is what we're going to do next, you'll see that we start to see some differences between finite difference and finite volume. But at least at this point, just evaluating the diffusion integral gives us the exact same coefficients as our finite differences. Okay. Right. Any questions on this?
Yeah, one question, Professor. On our third and fourth term of our equation, why was there a negative sign in front?
Yeah, that's a great question. So the third and the fourth term, so that was the west and the south integral. So remember that minus sign comes from the normal vector, right? Because remember, when we are evaluating these integrals, we have this dot n right here, okay? Where that dot n, that's the normal vector on that specific face, okay? So if we kind of draw our square again, okay? And then let me take a pen here. Okay. So the normal vectors on basically each of the faces represent, basically the directions that face kind of outward, right? So for the north and the east faces, the vectors point up and to the right. So those are positive directions. So one's in the positive x direction, the other's in the positive y direction. But for the west and the south, they point to the left and then down. So the left basically is a negative x direction, and then the south is the negative y direction. So that's why we have these negatives that come out.
Okay.
Yeah.
Thank you.
Okay, any more questions on this?
So just to be clear, we're kind of treating it like an axis, the positive x and y coordinates.
Yeah, exactly. Yeah, so we're basically obeying the same coordinate axes that we're putting on. So if we put kind of a weird axis on this, then you'd have to kind of respect that too. But we're basically putting just a standard axis on these.
Okay, thank you.
All right, any more questions on this before we do boundary conditions? Okay, so let's go ahead and do that. Oh, actually, one more thing. So we have to actually plug this back in because that was just the diffusion integral. But if we plug this back into our equation, we also had our source term. So let's just do that really quick, right? So let me integrate the source term really quick because it's pretty easy. Right, so our source integral looks like this. So we had our source function q of x and y integrated on dA. Okay, and then what we're basically going to do is we're just going to apply trapezoidal rule on this directly. So we're not going to do any divergence theorem, basically because there's no derivatives here. We basically just have a function. Okay. So if we do that, we basically get q of xc, yc. Okay. So we're going to be evaluating the source term at the centroid of our cell. So basically that's the same as our 1D case. And then we're going to multiply it by the area of the cell. So if we assume kind of a uniform grid spacing, our area is going to be just delta squared. Okay. So if we plug that back in, we get the equation that we can actually use to form algebraic equations, right? remember our goal with finite volumes is to get, or any finite method is to get an algebraic equation from a differential one. Okay? Okay. So there's basically our algebraic equation. So on the left-hand side, we have our diffusion integral, which is what we did on the last board. And then finally, on the right-hand side, we have the integration of our source term, which is q xc yc, which is the x and y coordinates of the centroid of the cell, multiplied by the area, which is delta squared. Okay. Okay. So actually, let me box this one because this is the one we'll actually use for the example. Okay. All right. So then now let's start to do boundary conditions. So just like if you remember from our 1D case, the thing that's different about finite volumes is that the boundary conditions, they don't actually become equations, but the boundary conditions just modify this equation. Okay. So I think before the spring break, we basically saw how this works in 1D. So let's see how it works in 2D. Okay. So in 2D, things get a little bit complicated because we have, we can have boundary conditions on basically all four sides of our cell. So, you kind of have to do this kind of a few times yourself to kind of be comfortable with the process. But let me do one example with the Dirichlet and then one example with a Neumann condition. Okay? So let's do a Dirichlet condition, and then let's assume that our Dirichlet conditions on the left. Okay? So let's say that we have a situation that looks like this. Okay. Okay. So let's say that we have a boundary condition that looks like this. So we have our phi c right there. And then on this left side, which I gave myself no room for, we have our prescribed value.
I'm sorry, Professor. That equation that we boxed is just a diffusion equation, correct?
Yeah. So that's the diffusion equation with the source term. So we're going to do an example basically after we do the boundary conditions, and we're basically going to apply this one directly to that. Okay. So remember, for Dirichlet boundary conditions, we're prescribing the solution value exactly. So that's why I have a phi naught here. So that phi naught is basically something that we're going to prescribe ourselves. Okay? So that's usually some number that I'm going to give you, like either 50 or 25 or something like that. Okay? So if we basically apply this, basically what that tells us is that the integral on the west face is going to be affected by this Dirichlet boundary condition. Okay? But all the other integrals are not going to be affected. So only the west integral affected. Okay. Because you can see for this case, for phi c, we have our north neighbor as usual, we have our south neighbor as usual, and we have our east neighbor. So we can evaluate those integrals basically the same as we did before, but the only one we can't do is the west because we don't have a neighbor on the west. And so what we're going to do is we're going to replace the west integral with an expression that incorporates the Dirichlet boundary condition. Okay. All right. Any questions on this before I wipe the board? Okay. Okay. So let's go ahead and do that out. All right, so let's write out basically our diffusion equation, but kind of one step up, kind of before we start replacing the derivatives. Okay. So our diffusion integral looks like this. So we have minus k times d phi dx on the east face multiplied by delta y plus d phi dy on the north face delta x minus d phi dx on the west face delta y minus d phi dy on the south face delta x. Okay. And so for this Dirichlet boundary condition, we know that the only integral that's going to be affected is the west one. Okay. So it's only going to be this guy. And so let's take this and let's replace it with something that's going to reflect the Dirichlet boundary condition. Okay. So before, what we did was we replaced this integral with phi sub c minus phi sub w divided by delta x. Okay. But if we replace this with the Dirichlet boundary condition, it's going to have this expression here. Okay. So we're going to take phi sub c just like we did before, right? But instead of subtracting the self-centered value from the west neighbor, let's subtract our prescribed value. Okay. So we have phi sub c minus phi sub, or phi naught, basically, which is something that we know. Okay. So this phi naught right here is our prescribed value. Okay. And then what we need to do is we need to divide this by the space in between the self-centered value and the face. Okay. So normally we divide this by delta x, since there's a length of delta x between cell centers. But since we're doing this at the boundary is only half that distance. So let's divide by delta x divided by 2. Okay. So then if you plug this in and then do a lot of the algebra, you end up with the following expression. Okay. Bringing in the source term too. So basically what's going to happen is this 2 right here is basically going to kind of add basically another value for phi c, and then that's going to move this to the right-hand side, okay? Our prescribed value to the right-hand side. So let me show you what I mean. So we get minus k times phi e plus phi n plus phi south, okay? So remember, just like we mentioned, all the other integrals are basically unaffected. So we still have phi e, phi north, phi south, basically exactly the same as we did. Okay. Okay. So normally for our our typical interior case, we have just a minus 4 phi c. But since we have this 2 right here, okay, that basically adds kind of an additional phi c on that side. So instead of minus 4, we have minus 5. Okay. And then on the right-hand side, we have q of xc, yc, okay, delta squared. So that's the same as before. So our source term is basically the same. Okay. Okay. And then to that, we're going to add our prescribed Dirichlet value. Okay. Because remember, the way that we formulate these equations, that everything that we don't know yet, we put on the left-hand side, and everything that we do know, we put on the right. So since our prescribed value is something that we know kind of beforehand, before we solve the problem, we can put that on the right-hand side. Okay? Where once again, we have this coefficient of 2. Oops. That's disgusting. Let me erase that. We have this coefficient of 2 in front right there, basically relating to the fact that we had we divided by the half distance right here. Okay. So basically that 2 and those 2 are related. Okay. My iPad is not being cooperative right now. Okay. So this is basically the equation that you would get for a Dirichlet condition on the west side. Okay. So make sure you kind of, when you're doing, the homework yourself, make sure you kind of go through this process, because depending on if your boundary conditions on the north, the south, or the east face, this equation is going to be kind of slightly different. Okay. But just to kind of give you just some general trends, what you should notice on the left-hand side here is that there's no phi w, right? Since we don't have a west neighbor, then that value shouldn't appear on the left-hand side. We had to modify the value for phi sub c. Okay. So basically, this value right here, this coefficient is changed as a result of the Dirichlet boundary condition. And then the other thing is, that Dirichlet condition has to show up on the right-hand side in some way, shape, or form. Okay? So in this case, it showed up on the right-hand side in the form of 2 times k times phi naught. But depending on which face you are, and especially once we get to convection, that the form on the right-hand side might be a bit different. So I think for diffusion, it's always going to be a plus, 2 times k times the phi naught. But when we get to convection, you'll see that this becomes a bit more complicated. Okay. All right. Any questions on this?
Professor?
Yeah.
At the end of the equation, is that 2 times k?
Yeah, that's 2 times k.
Mm-hmm. Okay. Thank you.
One more question. What was the reason for dividing by 2?
Right. So the normally, when we have a west neighbor, right? So if I can draw this. Right. Basically, what we assume is that this distance in between the cell centers is delta x. Okay. But since we're on the Dirichlet boundary, we're not going all the way to the west neighbor since there's basically no one there. Okay. So basically, what we're doing is we're only going this distance right here, from the center of our cell over to the west boundary. So if we say delta x is the distance between cell centers like that, then the distance between our center and the boundary is just delta x over.
Oh, I see.
Yeah. Mm-hmm.
Okay, thank you.
Mm-hmm. Yeah. Any more questions on this before we do Neumann conditions? Okay. Oh, question? Oh, okay. Okay. So let's do Neumann conditions, right? So the nice thing about finite volumes is that Neumann conditions become a little bit simpler compared to Dirichlet. Okay? Because Neumann conditions, what we're going to do is we're going to basically replace an entire derivative. Okay? So let's do an example where we have a Neumann condition on the south face. Or let's do one on the north because that's kind of consistent with our example here. Okay, so we have, since we have a Neumann condition on the north, we have neighbors on the west, the east, and the south. Okay. Okay, and then let's say our Neumann condition on the north side is equal to gamma. Okay. So just like before, we're going to start with the form which has all the derivatives at each of the faces. Okay. So we have minus k times d phi dx on the east face, delta y, plus d phi dy on the north face, delta x, minus d phi dx on the west face, delta y, minus d phi dy on the south face, delta x. Okay. And so what we're going to do for the Neumann condition is we're going to take basically this entire thing, the derivative on the north face, and basically we're just going to replace that with gamma. Okay. Because remember, the Neumann condition is we're prescribing basically the derivative at that boundary. Okay, and then kind of just naturally through our finite volume formulation, we get these expressions where we have the basically we're evaluating these derivatives on each of the boundaries of our cell. Okay, so basically what we can do is we can take basically that entire thing that I've highlighted and just replace it with gamma, and then that becomes our Neumann condition. Okay, so let's go ahead and just work through the math for that. So for everything else, we're going to plug in basically our normal expression. Okay, so all other integrals unchanged. Okay. Right. So then if we do that and we kind of work through all the kind of the algebra, we're left with this expression. Okay, so we get minus k phi sub e plus phi w plus phi south, right? Because remember these, you know, those are the those come from the integrals on the west, on the east, west, and the south faces, so those are unchanged. Okay. Okay. And so since we're basically replacing that entire derivative with our gamma, then what that does is it affects our value again. Okay. Because remember for the interior case with basically no boundary condition, that's a -4. But in a Neumann condition, that becomes a -3. So we basically kind of you know, lower the value of that coefficient. Okay. Okay. So that's everything on the left-hand side. Okay. And then on the right-hand side, we have our source term like usual. So we have q of xc yc multiplied by delta squared. Okay. Right. And then we have to add the effect of our Neumann boundary condition. So in this case, we add a plus k delta gamma. Okay. Okay. So the reason it's plus is because you see we have a basically a minus right here. So that minus multiplies by that, and then we move it to the right so that becomes a positive. Okay. Question?
So on your notes, you have it on the south side. So originally our equations would be north minus center.
Mm-hmm.
So that's why when you bring it over to the other side, you have it positive on your notes. Since you did the Neumann on the south, everything would just be the opposite.
Right. Yeah. So actually, there's a typo in my notes. So on the notes, I basically say it's, you know, I did it for the south face, and this plus right here in front of the k gamma delta, that's a this was a minus in the notes. Okay. So that the sign of that thing was basically a minus, and I basically said that it's always minus. But you know, after I did some more examples, I found out that that's not true. So this sign, this is something that you have to choose pretty carefully. So when you move this term over to the right, it really depends on which face that you're solving. Okay? So for if you're doing it on the north and the east face, you're going to have a positive. Okay. But then if your Neumann condition is on the south, like it is in the notes online, or if it's on the west, then this is going to be negative. So the Neumann, you have to be really careful. So you have to basically make sure you assign the right sign on the right-hand side, basically on whichever condition that you're doing. Okay. Okay. And the other thing to note with the Neumann condition is that we have an additional delta here. Okay. So remember that wasn't present in our Dirichlet condition because basically everything canceled out. But so make sure you include that delta, especially when you're implementing this in code. All right, any last questions on this before we jump into an example? Okay. So let's do an example. All right. So in this example, let's solve this this equation. So we'll have d squared phi dx squared plus d squared phi dy squared. Right. This is equal to 3xy. Okay. So we have a fairly simple equation. So here in this case, k is going to be -1. And then our q is 3xy. Okay. And then we want to solve this on the following domain. Okay. Let me move it to the right a little bit so I can write the boundary conditions. Okay. So we have our square domain like we usually do. Right, so on the left side, we have a Dirichlet condition of 50. So we have phi naught is equal to 50. On the bottom, we have a Dirichlet condition of 25. On the right-hand side, we have a Neumann condition of 0. So we basically have no flux out the right-hand side. Okay. And then on the top, we have a Neumann condition of 10. So basically, our derivative up there is going to be equal to 10. And so the way that we're going to discretize this is we're going to discretize this into 16 finite volumes. Okay. Okay, so our 16 finite volumes are given by that. Okay, so like a really bad connect forward board. Okay, so basically what we're going to do is we're going to apply our basically the equations that we developed previously, and then write out the equations. Okay, and then after we write out the equations, we're going to see how this is implemented in Matlab. Okay. So I'm pretty sure the script should be posted on Matlab or on Titanium. But I have it opened up on my computer too. So if you don't have MATLAB ready, you can basically just follow along what I'm going to do. All right, so are there any questions about the problem setup? Okay, so let's start writing things by hand, okay? So we basically, we're gonna progress through this basically kind of the same way we did our finite difference problem. So first thing we're gonna do is we're gonna write out the equations for all the interior cells, because the interior cells are kind of, they all kind of follow one rule. And then for all the boundary cells, probably we won't have time to do all of them, but I'll show you how to do at least, a couple examples of Dirichlet and a couple examples of Neumann, just so you can kind of see, how I develop these equations. Okay? So first, let's do the interior cells. Okay. And then after that, we'll do the boundary cells. Okay. Okay. So for the interior, basically, they all follow the same rule. Okay, so they're going to follow this equation right here. So we have minus k phi plus phi n plus phi w plus phi south minus 4 phi c. Okay. Right, and that's going to be equal to our source function times delta squared. Okay. So basically all we need to do is basically apply this to any of the interior nodes, okay? Our interior cells. So our interior cells in this case are going to be 6, 7, 10, and 11. So let me highlight those for you. Okay. So all the cells that I've highlighted are basically ones that are on the interior, okay? And basically, if you're kind of wondering which ones are the interiors and which ones are not, the interior cell should have neighbors basically on all sides. Okay, so it shouldn't be touching a boundary at all. So you can see cell 6 has kind of follows this criteria. So it has a neighbor on the east, which is cell 7, has a neighbor on the north, which is 10, has a neighbor on the west, which is 5, and it also has a neighbor on the south, which is 2. Okay, so let's write out that equation. Okay, so for cell 6, we have the following equation. So we have minus k. And let's actually just fill in k right now. So we know k is equal to minus 1, right? Right. So since we know that k is minus 1, then we can just kind of plug that in. So minus times minus 1 is just going to be positive. Okay. So for cell 6, we have phi east. Phi east is going to be phi 7. Okay. Plus phi north. Phi north for 6 is going to be phi 10. Next is going to be phi west, which is going to be phi 5. Right.
Excuse me, Professor.
Yeah.
How do you know k was equal to -1? Was that like a given that's like given in the problem, or we had to figure that out?
Yeah. So in the problem here, this equation right here is always going to be given to you, or I would give it to you in the homework. Oh my God. Okay. So basically, whenever you do a problem, you always have to start with some equation that has to be given to you. And since there's basically a coefficient of 1 out here, So in order for that to be 1 out there, then k has to be -1 to kind of match up with our, you know, our general form. Right? But yeah, that's always going to be given to you basically from the problem. And you can just pick it up right off from the equation.
So if there's a coefficient in front, like +3, then our k would equal -3?
Yep, exactly.
Okay. Okay, thank you.
Mm-hmm. All right, so then our south neighbor in this case is going to be phi2, okay? And then phi c in this case, which is our south, is going to be phi6, okay? Okay. And then, you know, then we're going to multiply by the source function, which is 3xy. So we have 3 times xc times yc, and then we're going to multiply by the grid spacing squared. So that's basically an example of an interior cell. So I'm not going to do 7 and 10 and 11 because they're kind of the same. So as long as you can pick out kind of which neighbor is which and kind of plug those into the equations, then they all kind of follow the same trend. Okay. All right. Any questions on this before we do some of the boundary cells? Okay. Okay. So now let's do an example with a Dirichlet boundary. Okay. So let's do, oh, I lost it. Let's do cell number 5, because cell number 5 has a Dirichlet boundary condition on the left. Okay. So remember, whenever we have a Dirichlet, or whenever we have any kind of boundary condition in finite volumes, we're going to replace that integral on that face with with an expression that incorporates the boundary condition. Okay. So in this case, on the west face, we're going to replace this this expression right here. Okay. Because normally, you know, we evaluate this using the west neighbor and ourself, but since we don't have a west neighbor, we need to evaluate this using the boundary condition. So just like we did with the kind of the example earlier, we're going to replace it with phi c minus phi naught all over delta x divided by 2. Okay. And remember, we divide by 2 because it's there's only a half distance in between the south center and the west boundary. Okay. Okay. So then if we plug that in, then we get basically the same expression that we did before. So we have minus k, which is just 1, okay, plus phi e plus phi north plus phi south minus 3 phi, or 5, sorry, 5 phi c is equal to q delta squared plus 2 times k phi naught. Okay. All right.
Hey, Professor, a quick question.
Yeah.
So for our Newman, you said that that sign would change if we're on the north and east compared to as if we were to the west and south. Is that the same thing for Dirichlet?
Yeah. So for Dirichlet, actually, it doesn't change because we have kind of a double negative. Because remember, we have the plus and the minus depending on which side that we're on. So that applies for the Neumann too. But remember, the other thing that we have is we have the order of these expressions here. That changes depending on whether we're on the east or the west or the north and the south. And so because of that, we have those two negatives kind of cancel out, so that this the sign of this guy right here on the right, this is basically always going to be positive for a Dirichlet boundary condition.
Okay, I just wanted to make sure.
Yeah, it's tricky. It's tricky, definitely. You have to kind of be careful with this. So you know, we're doing some kind of together like this, but when you kind of do this yourself, definitely try to work it through, just so you know. Okay. Okay. So we can go ahead and plug that stuff in. Okay. So for phi 5, we basically get phi e. So phi e, the east neighbor for 5 is going to be 6. We have phi 6. Plus the north neighbor, which is going to be 9, plus the south neighbor, which is 1, okay, minus 5 phi c, okay, is equal to 3 xc yc delta squared, plus 2 times k. where k is -1, right, times phi naught, where phi naught in that case is 50. Okay. Right. So that right there, this is your equation for cell 5. Okay. So you can see we're kind of progressing in the same way as we did before, where you know, we're basically going to get an equation for every cell in our grid. Okay. All right. Any questions on the Dirichlet condition? Okay, so let's do a Neumann condition now. So let's do cell 14, because 14 is on the north face. Okay. So we have the same deal here. So so for the Neumann condition, we're basically going to replace the integral that corresponds to that boundary with that Neumann condition. Okay. So for cell 14, which kind of borders the north boundary condition, we have phi d phi dy on the north face, delta x. Okay. So we're going to place this entire derivative with the Neumann condition, which is gamma, and then we're going to multiply by delta x. Okay. So if we incorporate this into our equations, then we can get a similar equation like we did up there. Okay. All right. Any questions on this before I wipe the board? Okay. So I'm gonna go a little bit quickly just because we're running a bit out of time, and I want to make sure I look at the Matlab code with you. Okay. So for cell 14, we get let's see, phi west, which is 13, plus phi east, which is 15, plus the south face, which is 10, minus 3 phi 14. Okay, is equal to 3 x c y c delta squared. Okay. And then we are going to plus, because this is the north face, then we have our gamma value, which is 10, times times our k, which is -1, okay, times delta, which is our grid spacing. Okay. So this right here, this is our equation for cell 14. Okay. Okay. So that was an example of a Dirichlet condition. That's an example of a Neumann condition. So what if we have a cell at the corners? Oh,
Wouldn't
question?
it be times k and your k value is -1?
Oh yeah, sorry. This is should be -1. Yeah.
Oh,
Thank you.
Mm-hmm.
Okay. So let's do a cell in the corner now, because remember when we did our finite differences, we could basically just ignore the corners. So unfortunately for finite volumes, we can't ignore the corners. And actually, you know, the corners are a bit tricky because the corners border two boundaries. Okay? So for the corners, what we need to do is we need to replace two of the integrals. Okay? So let's do cell 1. So for cell 1, we have a boundary condition on the west face and on the south face. Okay? So we're going to need to replace both of these integrals. Okay? So for cell 1, basically we have two Dirichlet boundary conditions. Okay. So we're going to replace d phi dy on the south face. Okay. Okay. So this is going to be phi c minus phi naught, where phi naught's our Dirichlet value. I'll divide by delta y over 2. Okay. Times delta x. Okay. Okay, and then we're
For
going to
south, wouldn't it be delta y?
It's delta y on the bottom, but we multiply by delta x outside. Because remember that delta x comes from the trapezoidal rule. That's basically the length of that south face.
Okay.
Yeah.
Okay.
Yeah. So for the west face, it's d phi dx, but then we multiply by delta y because that's that west face is basically a vertical face like this. So the distance right there is delta y. I mean, in the end, we assume delta x is equal to delta y, so they cancel out. But it's good to kind of remember kind of where each of them come from. Okay. Okay, so we're going to basically do two replacements here. Okay, so we're going to replace both of these guys. So if we do that, we're left with the following. So for cell 1, we basically only have the east neighbor, which is 2, and we have the north neighbor, which is 5. Okay, and then we subtract the coefficient for phi 1. But since we have kind of two replacements here, our coefficient in front of phi 1 is going to be 6 instead of 4 or 5. Okay, so this is the equation for 1. And then on the right-hand side, we have our source term like usual, so 3xc yc delta squared plus our two Dirichlet conditions. Okay? So we have 2 times k times the first Dirichlet, which is 25, plus 2 times k times our other Dirichlet, which is 50. Okay? So when you're dealing with the corner cells, you need to basically do this twice for basically both the boundary conditions. So in this case, we have a Dirichlet and 2 Dirichlets, but you need to watch out for if you have kind of a Dirichlet and a Neumann or 2 Neumanns, and you should make the appropriate adjustments. Okay?
So piggybacking off what you just said, if we had a Dirichlet and a Neumann like corner 13, it would be, when we bring it to the other side, it would be plus 2 times negative 1 times 50. And then since we're on the north, it'd be plus 2 times gamma times delta.
There's no 2, but yeah, you got all the signs right. So on the last Neumann term, it should be plus gamma, which is 10, times delta. Yeah.
Okay. And then times negative 1, right? Because of the k.
Yeah, and times negative 1. Correct.
Okay. Cool.
All right. Any more questions before we jump into MATLAB? Okay, so let me share my laptop screen.
Professor, you're gonna do you have cell 13 on computed on your notes online?
Yeah, so online I have all the cells computed, so you can look at those values.
All right, thank you.
Okay, so here you can see my screen, hopefully. Right? So since we're almost out of time, I kind of want to just go through this kind of quickly, right? So section 1 of the code is basically the same as basically all section 1. So here we basically are just defining all of our variables, okay? So we have the length of the domain, we have the nx, which is the number of cells in the x, number of cells in the y, okay? Then we compute our total number, and then we have dx, dy, which is our grid spacing, and then we have our matrices right here, okay? And then just like we did by the hand calculations, we set our k value here to -1, okay? All right, so then now let's kind of go into the meat of the code, which is this section 2. So in section 2, we're basically going to be looping over all the x and the y values, okay? Or x and the y cells, okay? So this first loop for 4I is equal to from 1 to nx. This is visiting all cells in the x direction. Okay. And then for the other loop, 4j is equal to 1 to ny. This is visiting all cells in y direction. So notice how these cells are nested. So, this is basically the same format as we always did. So when you do kind of these loops in combination, where you put the second loop inside the first loop, through this we can visit every single cell in our grid, okay? Which is what we want, because basically what we want is we want to basically form an equation for every single cell. So in order to do that, you have to visit every single cell in our grid. Okay? Okay, so then the next code block here, we compute our ID numbers. So this is standard for all of our 2D problems. So for every 2D problem, we have to compute the ID numbers for yourself, for the cell of interest. That's usually my ID. And then we have our ID numbers for the west, the east, the north, and the south. Okay? So this code block is basically pretty standard. We use this basically in all our 2D codes to compute the ID numbers. Okay. So then now we start to move into computing the other all the other terms. Okay. So the way I've kind of structured this is we need to check basically if we're on an x boundary or the y boundary. Okay. Or the left or the right or the top and the bottom boundary. So that's what these if statements are for. Okay. So you can see this first if statement here. We have if I is equal 1. This tells us we're on the west boundary. Okay. So on the west boundary, we know that we have a Dirichlet boundary condition. Okay. So in that case, we apply the coefficients like we need to. Okay. So if you notice here, first we have the coefficient for the diagonal term. So this is a at my ID. So this is the same as the coefficient for phi sub c. Okay. So you can see here, I kind of have it backwards a little bit. I think because I have kind of an extra negative floating right here. But you can see, we know that if we have the Dirichlet boundary condition, our k value is going to be 5 in the end, right? But in this if statement right here, all I'm doing is basically considering the horizontal component. So I'm basically computing the west and the east integrals at the same time. Okay. So since we're only computing the west and the east integrals, then our base case in this case, which is down here. Okay. So since we're just doing the west and the east integrals, the only thing that we're doing is 2 of them. So in the base case, we have a neighbor on the east and the west. We're only going to add 2k right here. Okay. So normally this is 4 if we're considering the north and the south, but the north and the south come down here. But since we're doing just the east and the west first, we're just going to add 2. Okay. So in this case, see, for the Dirichlet boundary condition, we're only adding 3 instead of 2. Okay. So just like before, we increase the coefficient for yourself by 1. Okay. And then you bring the Dirichlet boundary condition on the right side. Okay. All right. So that's that covers our base case for the east and the west integrals, and then also the condition for our Dirichlet on the west side. Okay. So on the east boundary, we have a Neumann condition. So on the east side, basically, we have to make the adjustments based on that Neumann condition. So you can see here, I've basically multiplied, or I've subtracted 1 from the diagonal component. So instead of a positive 2k, I just have a single k here. Okay. And then for the coefficient for the west neighbor, we have just a minus k, right? Okay. Okay. And then this is a typo, so this should be a plus. And then since on the east boundary condition, we have a Neumann condition, we basically are going to add that component, because remember, we're on the east face. And we're going to do k times the Neumann value, which is just 0 in this case, times delta y. Okay. All right. So that takes care of the east and the west integrals. So now let's do the north and the south. So if j is equal to 1, this is our south boundary. So you can see for the south boundary, we have a Dirichlet condition. Okay. So this looks the same as it did up there. So for the Dirichlet, we're going to, instead of a 2k, we're going to add a 3k right here, because we increase it by 1 for the Dirichlet boundary condition. And then for the north neighbor coefficient, we have just a minus k. Because remember, if we're on the south boundary, we don't have a south neighbor. So we only need to add a coefficient for the north right here. Okay. And then on the right-hand side, we add our Dirichlet boundary condition like this. Okay. And then for the north, this is a typo. Okay, so for the north boundary, is the same as basically up there. So we have a positive k, only 1 right here because we have a Neumann condition. Okay. And then for the south, since we have a south neighbor, this is the same as before. So we have a minus k. And then we add a 10 which is our Neumann condition, times k times dx. And then here's our base case. So for the base case where we have both the north and the south neighbor, we have a 2k. That's kind of the standard. And then we have a minus k on the south, and then a minus k on the north. Okay. Right. And then in addition to that, we have the forcing function here, where again, remember we use xpos and ypos. This is for the cell centers. Okay. So the rest of the code is basically pretty standard. We solve the system, and then we plot it. So if we run the code, okay, we get our solution that looks like this. So I ran this with 100 by 100, so this is fairly big, but you can tone this down basically as much as you want. Okay. Okay. So I know that was really fast, but you guys can use this code here as basically as a template for for doing the homework. So you should have everything you need to go. So we're out of time for today. So I'm not going to keep you guys, any longer. But just like before, the recording of this lecture is going to be up on YouTube by tomorrow morning. So I have to give another lecture right now, and then I basically spend the night processing the video, and then I'll upload it tomorrow. Okay? So that's it for today. So thank you guys for coming in. So just like we talked about, so on Wednesday I'll have new starter code for the project. And I will go over the project code kind of together, so that to kind of give you guys kind of a few kind of helpful hints with that. Okay. So I'll see you guys on Wednesday. And if you have any questions on anything, definitely let me know. I'll try to be as active as I can with emails, or if you want to talk, I can set up a Zoom meeting for you guys too. Okay. So stay safe, stay healthy, everyone, and I'll see you guys on Wednesday. If you have any questions, I'll stick around for a few minutes, but I can't stick around for too long because I have another lecture after this. Okay, I'll see you guys on Wednesday.